So I'll introduce our next speaker, Chris Blake. Chris has worked at Maya HTT for 13 years as an application engineer and later as a manager of engineering services. He engaged with clients from numerous industries: aerospace, automotive, high-tech electronics, and AC HVAC, to define their simulation requirements and execute thermal CFD analysis to optimize their designs. As a senior solutions architect, he managed large custom software development and PLM deployment projects in order to make companies more efficient and effective. Now, as director of new product development, he explores new technologies such as building information modeling, cloud-based simulation and artificial intelligence and machine learning, evaluating technological readiness, go-to-market strategy, and industry applicability. Chris holds a bachelor's degree in systems design engineering from the University of Waterloo and a master's degree in mechanical engineering from McGill University, having completed a thesis on the topic of satellite formation, flying, and control. Chris is also an alumnus of the International Space University. Oh, nice. So am I. And with this, Chris, if you want to share your presentation, thank you.
Sure. Thank you very much for that introduction, Olivia. Good afternoon, everyone. My name is Chris Blake, Director of New Product Development with Maya HTT. So over the past several years, we have, as a company, engaged with several major gas turbine OEMs to implement tools for the thermomechanical modeling of their engines. However, as we proceeded, the industry challenges and the use cases driving their needs kind of revealed themselves. So today I'd like to present some of the research and development that we've done to tackle some of these use cases. So next. So in terms of an agenda, I'll start with a brief review of the gas turbine industry and some of those challenges, followed by the technology bricks that address those needs. I'll step through the research that we've conducted in each of those areas, and then I'll tie it all together with a digital twin use case. But first, just briefly about Maya HTT. Maya is a software development and engineering consultancy firm. We're based in Montreal, Canada. For over 30 years, we've been a strategic partner with Siemens Digital Industries Software. We've developed over 30 software solutions for their portfolio, including SimCenter 3D thermal multiphysics, which is widely used in the aircraft engine and power generation industries. But in addition, we provide services in design, manufacturing, simulation, PLM, custom development, and workflow automation, as well as applied artificial intelligence and IoT. So the gas turbine industry can essentially be divided into the propulsion business and the power generation business. When we talk about propulsion, we talk about aero engines like the turbofans on transatlantic aircraft. Engines can be commercial or for business or military vehicles, but they're not necessarily limited to airplanes. They can be for helicopters as well. When we talk about propulsion, the business model has changed over the years, based in no small part to the revolutionary power by the hour concept of Rolls-Royce. So essentially, engines aren't purchased anymore, but rather their uptime or their in-flight usage is purchased. So there's a strong incentive for the OEMs to maximize that uptime by remotely monitoring the state of their engine fleet and scheduling optimal maintenance interventions. The power generation market, on the other hand, are those gas turbines used to generate consumer electricity or power industrial plants and even offshore rigs. And traditionally, maintenance has been purchased as needed or via aftermarket maintenance plans. This is evolving into long-term maintenance plans with OEMs absorbing more of that responsibility. So remote monitoring and diagnostics are seen more and more as a value add. So if we focus more on the power generation market, we uncover a few interesting challenges. So first of all, the data scientists who are tasked with developing predictive models, they need a tool to gather and track data coming from both simulation sources and real world sources. The operations engineers need to know when it's safe to restart a turbine engine. or at what cost to the remaining useful life further utilization of that engine will have. When I say remaining useful life, that refers to the number of cycles that a specific part or maybe the entire engine can endure before maintenance or overhaul is required. And low cycle fatigue like creep or high cycle fatigue like rotational dynamics and vibration can contribute to this. And then there are the service engineers who just need to know the optimal time to perform those repairs. So what this all boils down to is the need to, first of all, federate data, monitor data, and augment the data. So the technology bricks that are needed to address these issues and challenges are as follows. First of all, you need a pipeline to capture and serve up the data to the other technology bricks in the stack here. Then you have thermomechanical simulation and test data correlation, which allows you to prepare a model that is going to confidently predict the transient engine behavior in reality. So that's our digital twin, basically. Then we have reduction techniques that produce models that can run more quickly and that can act as virtual sensors for the prediction of engine states that aren't necessarily that easy to measure. And then we have the cleansing of real-world engine telemetry data prior to sending it off to those virtual sensors, dashboards, alarms, and other pattern recognition or machine learning algorithms. If we look at it a different way, from the point of view of the data and process flow, the data pipeline in the middle consumes both the test and in-service data. But this data can be noisy and contain certain errors like sensor failures, so the detection of outliers and cleansing failures is necessary before serving up those data up to inline virtual sensors, correlation activities, dashboards, or even predictive maintenance algorithms. And then those virtual sensors are derived from the reduced order models of the detailed thermomechanical model. So now I'll just jump into some more of the technical details. When it comes to modeling a gas turbine engine, there are different levels of fidelity depending on the maturity of the program. You can have your system simulation all in 1D or model-based systems engineering. You can have 2D simplified whole engine models. Then you have full 2D complex whole engine models where you're simulating both the thermal and the mechanical behavior. Then you can have 3D component submodeling to get more detailed behavior still. And then on the high end, you have full 3D whole engine model simulations. These whole engine models are very complex and can include hundreds, if not thousands, of thermal boundary conditions. And so, though it's possible to include computational fluid dynamics, it is most common to represent gas and air flows in the engine using these advective streams and voids, where the temperature and mass flows are coming from upstream thermodynamic calculations. The engine is commonly modeled using a combination of 2D axisymmetric and 3D meshes. There are transient analyses over several mission profiles, as you can see in the graph at the bottom there. And stator and rotor temperatures, as well as the deformation of the engine blades, are computed. Now, these can be inputs for subsequent creep analyses, and this example that we're seeing right here is of a compressor stage that was modeled in SimCenter 3D using the Maya-authored thermal multiphysics solver. Now, these complex thermomechanical engine models need to be correlated to test data. Our clients have reported that doing so by hand is extremely lengthy and tedious endeavor. So we set out to develop a more automated method that searches the design space to minimize the difference between test and simulation telemetries. The key challenges are just the sheer number of design variables, as well as the fact that we're trying to correlate transient profiles, as well as doing so with a nonlinear model. Traditional perturbation methods to compute the sensitivity to design variables are way too expensive because you have to do it one by one. And so we've implemented an approach using the adjoint equations. With this approach, every design cycle, optimization cycle rather, involves 2 transient runs as opposed to 1 for each design variable. In the forward solution, we obtain the temperature field at each time step and then define the objective function, which is to minimize the error between the simulation and the test data. And then in the backward solution of the adjoint system, the gradients are computed and the design variables are updated. It's a bookkeeping exercise to keep track of all the gradients, and the optimization scheme chooses the largest step to take along the gradient direction within that design space. Our tests so far have shown that upwards of a 12 times speed up when using the optimization scheme over constant step size. And this scheme is general. It's not only applicable to gas turbines, but can be applied to general transient thermal models as well.
Hey, Chris, you have 1 minute left. Do you want me to move to a specific slide?
Oh, I have 1 minute left. We burnt so much with the technical issues. Well, I mean, we can zoom ahead to slide 13 and 14 if that's okay. We've been talking about the data collection with our data pipeline. When it comes to data cleansing, one of the things that we've been researching is into rules to identify and remove suspect data. And so we can use statistical methods like distribution entropy to determine whether there are sensor jams or whether a sensor has gone offline or there are too many repeated discrete values that will manifest itself in a graph like this as showing lower than expected entropy. We've also developed and researched outlier detection methods.
Is that correct?
To see, it's basically an unsupervised machine learning algorithm that detects outliers in a high dimensional telemetry data. So we can use a distance function from the statistical mean to see if there are any data points that are abnormal. And then we can define rules to automatically cleanse those. I guess if we're running out of time, I just want to mention that we can use model order reduction as well. And we've been doing intrusive methods to attract system matrices and project those onto a reduced order basis so that we can actually build reduced order models that will serve as virtual sensors. And those can be deployed either on the cloud, on the edge, or and basically in line with our data pipeline so that you can glean and start to develop predictive maintenance algorithms to help with the maintenance of these turbo machinery engines. So unfortunately, I ran out of time. It was the technical issues that we had sharing my screen. But if you just go ahead to the concluding slide, that's basically what I wanted to show today was that, simulation and AI are pervasive tools. We can augment AI data sets with CAE, but we need reliable data flow strategies so that we can feed our reduced order models and virtual sensors. And this basically enables new business models, energy as a service, or long-term maintenance plans. And if I ran too quickly and you need to ask any more questions, on the last slide, you see my email address and links to our company website if you need to find out more about what we're doing in this space. So thanks for your patience, and thank you, Olivia, for advancing the slides on my behalf.
No worries. Thank you very much, Chris, for your great presentation. And as you mentioned, if you have any questions for Chris, please feel free to drop him an email or reach out to him through the chat. Thank you.